Hi everyone. Today we are going to talk about Chapter 3 Phasors and Sinusoidal Steady-State Analysis. So this is the overview of the entire chapter. There are 5 sections. 3.1 is about sinusoids and phasors. 3.2 Phasor relationships for resistor, inductor and capacitance. 3.3 Impedance and admittance. 3.4 is the application of Kirchhoff law in AC circuit analysis. 3.5 is about AC steady-state analysis. So this is how AC power is transmitted from the power plant to our household. So you can see that power plant generates electricity, or in other words power, and when it goes through some transmission line and power substation, the main objective of this power substation is to step up or step down the current and voltage. So finally, the power would be transmitted to our household through these transmission wires. So this block diagram is basically similar to the diagram that I showed you just now. So the voltage generated by the power plant is about 18 kilowatt. So once it goes through a transformers, it will be stepped up to 350 kilowatt, and the current will be stepped down at the same time. So after going through the transmission lines, it will reach another transformers again, and this transformer will step down the voltage to 18 kilowatt, and it will be distributed through some transmission wires. And before reaching our house, our residential areas, it will go through another transformers again, which would step down the voltage further to 230 watts. So an AC voltage is actually a time-varying voltage, or AC current or voltage. They're the same. They are actually time-varying. So it can be represented using a sinusoid. It's given by the mathematical expression here. For voltage, it's the amplitude of the voltage times sine omega t plus theta, or the amplitude of the voltage times cosine omega t plus theta. So Vm is the amplitude of the sinusoid, which is the peak of the voltage. And this is actually an omega. Is the angular frequency in radian per second. Expressed in radian per second, omega t is the argument of the sinusoid, and angle is actually the phase shift of the waveform. So frequency is 1 over period. So it's actually inversely proportional to period. Let's talk about phase shift. Phase shift is the phase difference between the waveform and the reference axis, shown here. So if the waveform is at the left of the reference axis, it's actually leading. So we will put a plus sign. So if the waveforms after the reference axis, we'll put a negative sign to show that it's actually lagging the reference axis. Now here's how we compare two waveforms. So since V2 is ahead of V1 by theta, we would say that V2 is actually leading V1 by theta, which is the phase difference between V1 and V2. So if V1 and V2 happen to overlap each other, they happen to start and travel at the same time and end at the same time. So they would be having the same phase. We would say that V1 and V2 are in phase. In other words, theta, the phase difference between the two voltage, is 0. So these slides show us the relationship between sine and cosine, the trigonometric function, the trigonometric identities of sine and cosine, how we can change from sine to cosine. So basically the phase difference between sine and cosine is 90 degrees. Let's have a look at example 1. Now, from this mathematical expression, we can see that 12 is actually the amplitude of the voltage waveform, and it has a phase difference of 10 degrees. The angular velocity omega is 50 radian per second. So since period is the inverse the reciprocal or it is inversely proportional to the frequency, angular frequency. So you can see that 2 pi divided by omega would give us 0.1257 seconds. In other words, it takes about 0.1257 seconds to complete one cycle. And frequency is the reciprocal of period, which is 7.958 Hertz. So example 2, identify the phase angle between current and voltage here, shown in A, B, and C. So in A, we can see that after changing both current and voltage to the same trigonometric function, in this case, we are changing them to sine. We can see that the phase difference is about 110 degrees. And we can see that current is actually ahead of a voltage, or current leads voltage by 110 degrees. Alternatively, we can put it as voltage lags current by 110 degrees. Same goes to question B. In question B, we can see that voltage leads current by 160 degrees. Of course, we have to change the sign of both current and voltage to be the same before we compare their phase difference. Similarly, in question C, we have to change the sign for both current and voltage so that they are the same. So in this case, we are changing negative 2 cosine omega t minus 60 degrees to 2 sine omega t minus 150 degrees. So after changing the sign, we have to change the trigonometric function as well, from cosine to sine. So by having the same sign and same trigonometric function, we can compare both current and voltage. We can see that current and voltage are having the same phase. So in this case, current is in phase with the voltage, or both I and V are in phase. So phasors, what is phasors? Phasors is actually the time domain of the voltage or current. So phasors uses complex number to represent sinusoidal time varying quantities, reduces the operation of calculus to simple linear algebraic operation. So let's have a look at what's phasor here in detail. So there are actually 3 forms of expression for phasors. The first one is known as rectangular form, which is in complex form. You have a real and imaginary value. The second form is known as the polar form, where you have the magnitude and the angle. Same goes to the third form, exponential form, where you have magnitude and angle. Exponential to the power of j theta, where theta is the angle. So mathematically, this is how we can interchange rectangular form to polar form and or exponential forms. So this is how we can evaluate the complex numbers. So if you are asked to add 40, 50 degree plus 20, negative 30 degree and square root the whole mathematical expression, we would get 6.91 magnitude and 12.81 phase difference. Same goes to question B. Mathematically, we should change polar form into rectangular form first before we can add them together. So once we have added them, if we wish to perform division or multiplication, we would have to change into polar form. And we would be able to get the answer equals 0.565 magnitude and negative 160.13 degree. Phasor diagram is a graphical way of showing how the real and rectangular or the whole complex rectangular form is related. The horizontal axis actually shows us the real magnitude, and the vertical axis shows us the imaginary magnitude. And the phase difference is shown here. The angle between the real axis and this diagonal line, which is the actual voltage, complex voltage or current in this case. So we can see that the voltage V is actually leading current IM by phi and theta plus theta. And this slide shows us how we change from time domain into frequency domain or sinusoid. How we change from sinusoid to phasor. So basically, using phasor in mathematics would be more convenient than using sinusoid or time domain. The reason is because we can always, if you are performing differentiation in time domain, then you are actually multiplying j omega to the voltage in frequency domain. Similarly, if you are performing integration, if you are integrating the voltage in time domain, then in frequency domain it's basically voltage divided by j omega, where j is the imaginary, j equals square root of -1, which is the imaginary sign. So here's the summary between time domain and frequency domain of phasor. So Vt is the time domain or instantaneous representation. V is the phasor domain or frequency representation. Vt is time dependent. V is not time dependent. And Vt is always real with no complex term. V is generally a complex number. Phasor analysis applies only when frequency is constant, that is, two or more sinusoidal signals of the same frequency. So like I mentioned to you just now, the phasor diagram shows you the magnitude and the phase of a particular voltage or current. So in this case, in this diagram, you can see that V1 has a magnitude of Vm and the phase is theta. And V2 has a magnitude of Vm with a phase of 90 degree plus phi. Here's another example. Example 4. We are asked to change from sinusoid to phasor. So, since phasor only takes into account the phase and the magnitude, so all we need to do is to extract this information from the sinusoids. So for example, in A, 6, if we are to express this in polar form, it will be written as 6 magnitude with angle -40 degree. Same goes to B. It would be, we have to change it to cosine first, and then it can be expressed as 4 magnitude 140 degree phase. If we are to change this from phasor back to sinusoid, a similar approach can be used. First, we change the rectangular form into polar form, where we obtain 5 magnitude 126.87 degree, and from here we can express it into sinusoid form, which is 5 cosine omega t plus 126.87 degree. Of course, we are not sure the angular frequency here because the information is not given in the phasor form. Same goes to question B. We have to change this into polar form first, which gives us 8 magnitude 70 degree, and then from polar form we can change it back into sinusoid, which is 8 cosine omega t plus 70 degree. So example 6 asks us to find the sum of these two sinusoids of I1 and I2. So an easy way is to change this into polar form first. So I1 will be represented as 4 magnitude 30 degree, I2 5 magnitude -110 degree. And by adding them up, by changing them into rectangular form, we can add them up. And then changing it back into polar form, we have 3.218 magnitude -556.97 degree. So which can be expressed below in sinusoid form. The same concept applied in example 7. If we are to perform integration in time domain, basically in phasor form, we are dividing it by j omega. If we are to perform differentiation in phasor form, it's multiplying by j omega. So it will be much easier if we are to solve a problem in frequency domain or phasor form. So by changing the variables here, the expression into phasor form, all we need to do is to perform simple calculation, and we will be able to get 4.642, magnitude 143.2 degree for current. And in sinusoid form, it would be expressed at 4.642 cosine 2t plus 143.2 degree ampere. In section 3.2, I'm going to show you the phasor relationship among resistance, inductance, and capacitance. So this graph shows us the relationship between current and ampere across, current and voltage across a resistor. You can see that they are actually in phase. Both voltage and current are in phase for a resistor circuit. Mathematically, it can be expressed as V equals IR, which is Ohm's law. So both are actually in phase. Current and voltage are in phase. In example 8, you are asked to find the sinusoidal expression for the current with the given sinusoid voltage input if R equals 10. So using Ohm's law, we can easily find that V voltage divided by resistance 10 ohm, we would get current equals 2.5 cosine 377 t minus 30 degree. So the current through 2 kilo ohm resistor is 40 sine 1000 t plus 42 degree milliampere. So in sinusoidal expression, the voltage is found to be 80 cosine 1000 t minus 48 degree watt. If an inductor exists in a circuit, so by measuring the current across the inductor, the voltage across the inductor and the current flowing through the inductor, we can see that actually current is lagging voltage by 90 degree. So they are actually 90 degree out of phase. And voltage always leads current, or current lags voltage by 90 degree. So the reactance for inductance is given by omega L. So if we are asked to find the voltage and we are given inductance and current, so all we need to do is to first find the impedance, which is J omega L. So by multiplying omega, which is 1000, with 4 millihenry, we will get 4 ohm. And J is represented by 90 degree. So voltage equals current times impedance. So which is 530 degree multiplied by 490 degree. So voltage that we obtain, VL that we obtain, is 20 magnitude 120 degree watt. So in sinusoidal form is 20 cosine 1000 t plus 120 degree. If we are to measure the voltage across the capacitor and the current flowing through the capacitor, again we can see it's like inductance. We can see that there is a 90 degree phase shift. But unlike the inductors, in this case we can see that voltage is actually leading current by 90 degree instead of current leading voltage in the case of the inductance. So for capacitive elements, voltage and current are 90 degree out of phase, and in this case, for the case of the capacitive elements, current leads voltage by 90 degree. So here's an example. So the impedance of capacitor is given by J divided by omega C, which gives us 0.5 magnitude negative 90 degree ohm. So by multiplying impedance with current, we would obtain the voltage across the capacitor, which is 3 magnitude negative 150 degree phase shift. In sinusoidal form is 3 cosine 500 t minus 150 degree watt. So impedance is basically the voltage across an element divided by the current flowing through the element. So it's given by the symbol Z, and the unit is ohm. The reciprocal of impedance is given by the symbol Y, and it's known as the admittance. So the real part of the admittance is known as the conductance, and the imaginary part is known as the susceptance. Let's have a look at example 11. So this is a very simple circuit. From this circuit, we can easily find current I by finding the total impedance, which is the combination of 5 ohm and the impedance of the capacitance. So the total impedance is 5 minus j, 2.5 ohm. So having voltage 10 0 degree divided by total impedance, we will be able to find the current flowing through the entire circuit. So if we have to find the voltage across the capacitor, then it would be current I multiplied by the impedance of the capacitor. That would be 4.47, magnitude negative 63.39 degree watt. So this table shows a summary among the relationship of resistor, inductor and capacitor. Let's have a look at example 12. For the following pairs of voltages and currents given, determine whether the enclosed element is a capacitor, inductor or resistor. So from here you can see that there's a phase difference. Of course we have to change the trigonometric function first. Both of these have to be the same. So in I we change it to cosine, we would get a 20 degree. So we can see that 20 degree, the voltage here is 20 degree. And the current that we obtain is 20 degrees, so that they are both in phase, so it's actually a resistor. For B, we can see that there's a 90 degree phase difference, and current is lagging voltage, so it's an inductor. For C, again there's a 90 degree phase difference, but in this case current leads voltage, so it's a capacitor. Now whatever we have learned in DC circuit can actually be applied in AC circuits. So Kirchhoff law, KVL, Kirchhoff voltage law and Kirchhoff current law is that we learned in DC circuits can actually be applied here in AC circuit. The difference between method that we use in AC circuit is, in DC circuit is that it only involves real magnitude, while in AC circuit real and imaginary magnitude or rectangular form is involved in AC circuit. So in DC circuit we learned that resistor is real, but in AC circuit the impedance can be complex, which involve both real and imaginary parts. Same goes to voltage and current, they could be real and imaginary as well. So whatever we have learned in the DC circuit in part 1 and part 2 of the lectures can be applied in AC circuit. So if we are to merge the impedance in parallel, the same formulas is applied here, a similar formula. Again, I would like to stress that impedance is complex, while in DC circuit only real value is involved. So the method for current divider is the same. For delta Y and Y to delta transformation is also the same. It's actually much similar to the DC circuit, except again complex values are involved in this case for AC circuits. So let's have a look at example 13. We are asked to find the input impedance of this circuit. So we can see first we have to calculate the impedance of the capacitor, the inductor. Here, 2 millifarad capacitance, 10 millifarad capacitance, and 0.2 Henry impedance inductance. But all of these have to be, the impedance of these elements must be found first. Then by performing series, parallel, and then series them again, we will be able to find that the total input impedance is 3.22 minus J, 11.07 ohm. Similarly, in example 14, if you are asked to find V0, the voltage across the inductor, we have to find the element, the impedance of all elements first, and then we can perform voltage divider. And by doing so, we can see that V0 is 17.15 magnitude, 15.96 watt. In example 15, Y to delta transformation is involved. So after changing this circuit from Y into delta, we can merge all the impedance together, and we can see that the total impedance is actually 13.64, magnitude 4.2 degree ohm. So current is, from Ohm's law, we can see that voltage divided by total impedance would give us current I. That would be 3.67, magnitude negative 4.2 degree ampere. So here's a summary of the steps we need to apply to analyze AC circuits. First, we transform the circuit into phasor domain or frequency domain, and then we solve the problem by using all the circuit techniques that we have learned, such as nodal analysis, mesh analysis, Kirchhoff voltage law, Kirchhoff current law, Thevenin circuit, and Norton circuit, etc. Then we transform the phasor back into the time domain. So since various circuit analysis has already been introduced in the DC circuits, which is the earlier lectures, our major effort is now to illustrate with examples, illustrate these techniques with examples. So example 16 show a AC circuit which consists of an AC voltage and an AC current. So by using mesh analysis, we can see that there are three meshes here, mesh I1, mesh I2, and mesh I3. By using mesh analysis, we can find current I0, I0 equals negative 6.12 magnitude, negative 35.22 degree ampere. So this is another example of mesh analysis. In this case, supermesh is involved. So after performing mesh analysis, voltage V0, which is the voltage across the capacitor, negative J2 ohm, can be found as 9.756 magnitude, 222.32 degree volt. In this example, we are using nodal analysis to solve voltage across 4 ohm. So we can see that the two nodes are involved, V1 and V2. So by performing nodal analysis, we can see that V1 is V1, which is actually the voltage across 4 ohm, is 20.8 magnitude, negative 126.87 degree volt. Similarly, in this example, we are performing supernodal analysis. So by performing a when there is a voltage source exists between two nodes, then it can be removed temporarily out, and we can connect a wire between V1 and V2 so that a short circuit is formed. So these nodes connected between V1 and V2 is known as a supernode. This is what we have learned in DC analysis. So by performing nodal analysis for this supernode, we can see that V2 and V1 is found to be 31.41 magnitude, negative 87.18 degree volt, and V1 is 25.78 magnitude, negative 70.48 degree volt. Example 20 illustrates how to perform superposition on an AC circuit. So since we can see that there are three sources involved here, so we can actually break this circuit into three smaller circuits. The first one consists of only 10 volt only of this voltage source. The second one consists of only the current source, and the third one consists of the voltage source here of 5 volt. So by solving each of these circuits and adding up the voltage across the 1 ohm found from each of these circuits, we can see that the total voltage is negative 1 plus 2.5 cosine 2t minus 30.79 degree plus 2.33 cosine 5t minus 80 degree volt. Example 21 show an example how to perform source transformation. So we are changing this circuit, which originally consists of a voltage source. We are now changing it into a current source. So by dragging our 5 ohm out and putting it into parallel, we can use Ohm's law to change the voltage into current source. So now we can see that these two elements are now in parallel, so we can merge them. After merging them, we perform again source transformation by dragging out this element drag it out and put it into series into the circuit, and changing it from current source back into voltage source using Ohm's law. So the total voltage across 10 ohm can be found to be 5.519, magnitude negative 28 degree volt. So here's another example of source transformation. And the voltage that we found across the 80 ohm resistor is 3.615 cosine 10 to the power 5 t minus 40.6 degree volt. Thevenin's theorem involves Thevenin's voltage and Thevenin's impedance. So the same method is applied here, like the one that we use for DC analysis. First, to find Thevenin's impedance, we remove the voltage source by treating it as a short circuit. Then we can find Thevenin's impedance. And by removing the load here, A and B, we would have to find the voltage across these two nodes, A, B. That would be the Thevenin's voltage. So Thevenin's impedance is found to be 6.48 minus J 2.64 ohm. Thevenin's impedance is 37.95, magnitude 220.31 degree volt. So here's another example of Thevenin circuit. Again, we have to find Thevenin's impedance and Thevenin's voltage, and the answer is found here. Norton's theorem involves Norton's impedance and Norton's current. So Norton's impedance, this is like Thevenin's impedance. The same method is applied here. We have to remove the sources, and then we have to find the impedance. If it's a current source, we have to treat it like an open circuit. If it's a voltage source, we have to treat it like a short circuit. And by solving the impedance, by merging all the impedance elements, we will be able to find the impedance of the Norton impedance. To find Norton's current, we have to put a short circuit between terminal A and B. We have to put a wire here connecting them so that it's a short circuit. So the current flowing through this short circuit would be Norton current, IN. Here's another example of Norton's theorem. By solving Norton's impedance and Norton's current, we will be able to find that Zn, Norton's impedance, is 20 plus J 40 ohm, and Norton's current, which is solved using mesh analysis, is found to be 3 magnitude 60 degree phase ampere. That's the end of the chapter 3. Again, I would like to acknowledge that most of the elements here are extracted from Alexander Sadiko's book. Thank you.